At 6 p.m. on November 19, 1998, the radios of millions of rush hour commuters tuning in to NPR's signature news program, All Things Considered, suddenly went silent. The signals for CBS radio and TV, along with CNN's airport network, cut out. Drivers at thousands of Chevron gas stations couldn't use their credit cards. Neither could many Walmart shoppers. But perhaps the biggest disruption in communications was in pager services used by police detectives, emergency responders, and doctors. For an estimated 80 to 90% of customers using Paging Network Inc., their small pocket-sized devices stopped beeping. While some of the 40 to 50 million Americans who had pagers claimed they welcome a break from the constant beeping, others were in a jam. Hospitals weren't able to reach obstetricians and surgeons for patient emergencies. Police who used pagers as more of a private alternative to radios were out of touch with headquarters. Drug dealers lost touch with customers for hours. One spokesman for a Dallas-based pager company said it was the first time in 35 years that the devices had been out of service. The Atlantic would later dub the incident as the Great Pager Blackout of 1998. The communication blackouts were caused by a satellite 22,000 miles above the surface of the Earth that had suddenly stopped transmitting signals. The Galaxy 4 satellite was put into service in 1993. Owned by Pan Am Sat, a Connecticut-based satellite service provider, Galaxy 4 provided service in the C-band and Ku-band microwave frequencies to the continental United States. It was part of a network of Galaxy satellites manufactured by Hughes Space and Communications Company, HSC, in California that were used by cable, network TV, and radio customers. Some of America's most iconic corporations also use the systems for their private networks: Ford Motor Company, Microsoft Corp., Xerox Corp., Eli Lilly and Company, and New York Life Insurance Company. After a day of interruption, Pan Am Sat wrote off Galaxy 4 as a loss and brought a backup that was already in orbit, the Galaxy 6, into service. Meanwhile, the hunt was on for what had caused the predecessor's downfall. At first, solar weather was blamed. In the weeks preceding Galaxy 4's demise, the space around Earth had been bombarded with bursts of electromagnetic radiation from the sun over 90 times. Most of this radiation was produced by explosions on the surface of the sun. Sometimes these events result in solar flares, beams of super-energized photons like X-rays and gamma rays that can pack as much force as 10 million erupting volcanoes. The most destructive form of solar weather, however, is coronal mass ejections, in which, as the name suggests, part of the sun itself is hurled out into space. CMEs can balloon to massive sizes, taking up a quarter of space between Earth and the sun. But the Galaxy 4's telemetry told a different story, ruling out solar weather as the culprit. According to the data, the satellite's main computer, SCP-1, had caused system-wide failure when it shorted out. SCPs are satellite control processors that handle everything from altitude control to where the solar arrays and antenna are directed. Boeing 601 satellite models like the Galaxy 4 were equipped with two SCPs, a main one and a backup. When both fail, the satellite is deemed a total loss. In the case of Galaxy 4, its secondary SCP was out of commission. Why that happened remains an unsolved mystery as of the airing of this video. After reviewing the telemetry readouts from the Galaxy 4, engineers at Hughes ran a simulation of conditions on the satellite and discovered that the likely cause was due to a phenomenon known as tin whiskers. Tin whiskers are tiny crystalline protrusions 1/100th the width of a human hair that grow outward from the plane of a surface, not to be confused with a related but distinct phenomenon of dendrites which grow on the surface. These filaments can create a bridge between a relay terminal and its base, causing a circuit to short out, which was what Hughes engineers believe happened to the SCP-1 on Galaxy 4. Tin plating had been used in the Galaxy 4 satellite's electronics because it has many of the advantages needed for these components: the ability to be soldered, the ability to endure tensile stress or ductility, and electrical conductivity. Tin is also far more affordable than some of the alternatives such as gold or silver. Ironically, two other reasons tin is often the go-to material for electronics plating is its effectiveness as a protective material that can extend product longevity, neither of which happened in the case of the Galaxy 4. According to NASA, there is no single accepted explanation for what causes tin whiskers. There are a few theories though. One of the prevailing ones attributes the tiny metallic hair to residual stress, which itself can be caused by a number of factors including the plating process, the diffusion of substrate material into the plates, compressive stress that occurs by turning a screw, bending or stretching that occurs prior to mounting, other problems with how it was handled during installation, or differences in temperature between the plating and substrate materials. Galaxy 4 is not an isolated case. Tin whiskers are responsible for 7 other satellite failures between 1998 and 2002. 3 were total failures because both the primary and redundant SCPs failed. Among these 3 were 2 others in the Pan Am Sat network, the Galaxy 7 and Galaxy 3R. The other 4 satellites were only partial losses, since one of the redundant SCPs was not affected, remaining operational after the initial incident. Tin whiskers don't just happen in space. In 1986, the FDA issued a recall of multiple pacemaker models because whiskers on tin plating over a crystal component led to total loss of any output from the device. Tin whiskers also shorted out circuits in radar systems on an F-15 fighter jet in the mid-1980s, a Phoenix air-to-air missile in the mid to late 1980s, and a Patriot II missile in 2000. The year before, the Foxborough Company, a manufacturer that supplies parts to power generation facilities, including nuclear power plants, had to notify customers across the country that tin whiskers could affect contact insulator cards, which are used to maintain electrical separation between field devices and control systems. Tin whiskers were discovered in 1951. Finding a solution proved slow going according to the FDA, due to the complex nature of tin whisker growth. By 1974, 2 common solutions had been developed, either using another material or an alloy of tin for plating, or, after installation, heating the tin plate above its melting point to release the stress that causes the hair growth. Satellite manufacturers used another solution. Tin plates were covered in conformal coating, a type of thin polymer similar to wax that was meant to hold back any whiskers from forming. Yet for the Galaxy 4 satellite, that coating had been breached, giving the whiskers their window of opportunity to inflict maximum damage. In response, NASA launched a study that lasted over a decade, exploring whether polyurethane conformal coating, also known as Uralane 5750 or Aerethane 5750, as a more effective way in holding back whisker growth. After 11 years of sitting in ambient storage, NASA scientists reported that tin whiskers had not been able to penetrate Aerethane 5750 coating that was 0.02 of an inch thick. By then, Boeing satellite manufacturers had already opted for a simpler solution: nickel instead of tin for plating material. Nickel came at a hefty price though, an extra 100 to 200 pounds per payload. Given a cost of $200 million to $250 million per each lost satellite, it was no doubt worth it to avoid more satellites lost to tin whiskers.